Hello, I'm a presenter Yunjung. I'm going to present Self-Calibrating Neural Radiance Fields. This work is done by Yunjung, Seokjun An, Chris Choi, Animeshri Anand Kumar, Min Cho, and Jesh Park. NeRF, an abbreviation of Neural Radiance Fields, has dramatically impacted neural rendering processes. The model is designed to render view-dependent color and enable continuous rendering, suitable for novel view synthesis. Their model strongly relies on a photometric loss that targets to reduce the color difference between rendered images and their corresponding target images. NeRF has been attractive work due to its superiority in novel view synthesis tests. As a prerequisite of NeRF, the acquisition of camera information is necessary. However, camera calibration processes require costly global optimization steps and often fail to converge. Our goal is to remove the necessity of the pre-computed camera information by jointly optimizing camera parameters with NeRF network parameters. To reduce the gap between the camera model and real cameras, we introduce an additional nonlinear distortion model that reflects nonlinear noises in the cameras. Thus, the camera model consists of intrinsic, extrinsic, radial, and nonlinear distortion parameters. While training neural radiance fields, we subsequently extend learnable camera parameters to improve the stability of training. We first extend intrinsic and extrinsic parameters. We then add radial distortion parameters as learnable parameters. Eventually, we add nonlinear distortion parameters as learnable parameters. By ablation studies, we experimentally demonstrate that curriculum learning is helpful for optimizing our model. We have observed that a strong reliance on RGB color is often harmful to the calibration performance. Thus, we introduced an additional loss called projected ray distance loss. This loss enhances the geometric consistency of rays using correspondences. In detail, for each pair of images, we find correspondences to generate rays. Then, we mathematically seek the closest point pair from two generated rays. Finally, we project the closest points to each image to estimate the distance of the rays. Consequently, our model is feasible to reliably render scenes although no carefully calibrated camera information is used. Compared to NeRF, which is trained without COLMAP camera information, our model renders scenes much clearer. Besides, our model shows higher rendering qualities for all the scenes when the camera parameters are initialized by COLMAP. Moreover, our model results in a reduced projected ray distance loss after training, indicating our camera parameter optimization results in better camera information. For several scenes, our model trained from scratch even performs better than NeRF trained with COLMAP camera information. In addition, we have applied our algorithm on a different NeRF architecture since our module can be used for NeRF variants. Our algorithm improves NeRF++ with better camera information, resulting in higher rendering qualities. We expect further NeRF architectures could be improved if our algorithm was applied. We also render images that are captured by a fisheye lens. Since a fisheye lens includes larger distortions, our additional camera model benefits from the original radial camera model. We have manually captured sculptures on our campus to verify our hypothesis. The camera information is initialized by COLMAP and uses the NeRF++ backbone for rendering scenes. Our model renders much clearer images than the original NeRF++. The data and code are currently available on our project page. Please visit our project page for more information. This is all for our presentation. Thank you.